Hello and welcome to Introduction to Nanoscience and Technology. My name is Michael Escudi. I am Professor of Electrical Engineering at NC State. In this lecture, I'd like to begin to summarize what we know about the structure of atoms and discuss at least a little bit of the history that led us to this understanding. So let's begin with our notes. And I encourage you to write down what I write down in your own notebook. It will help with your memory and often help you form better questions. So let's begin with the understanding of physics in the early 1900s. And in particular, the view of classical physics. And the view of classical physics as it pertains to atoms really begins with electrons. And at that time, electrons were seen as nice particles. And by that I mean that an electron was seen to obey and observe the same kinds of laws as baseballs or any other particle, baseballs and bullets. And in short, they would obey what might be called classical mechanics. The kinds of mechanics that Isaac Newton would have understood from his point of view. And then it was understood that electrons behave this way both inside atoms as well as when they were apart from an atom, just by themselves. Now the second topic of understanding I'd like to point out to you is that in the early 1900s, it was understood that light itself was a wave. And as a wave, has a wavelength, a frequency, and a speed. And I hope you recall that these are all related by a relatively simple equation where c is the speed of light, f is the frequency, and lambda is the wavelength. And this matched very nicely the theory of electromagnetism that by this time was around 50 years old from James Clerk Maxwell of the Maxwell's equations fame. And so this is a very classical way to describe light and as waves and all of this. And also, of course, there's light itself. These light waves have energy. And they can carry energy, for example, from a light source to your eye or to some other object. All right, so they can certainly carry energy as waves, and they do so in a way that has something to do with the wavelength, but let me delay that discussion just a little bit and simply focus on the spectrum. So we have a common language for some of the features of light, and what I want to draw here is an axis of wavelength and identify for you the kinds of waves that are corresponding to those wavelengths. So radio waves, which I hope you've heard of before, are on the scale of meters. And microwaves, which are the electromagnetic wave, not the thing in your kitchen, have a wavelength on the scale of centimeters. And of course, the microwave in your kitchen employs these microwaves to excite the molecules in the food so that they heat up, but those wavelengths are on the scale of centimeters. And then if we keep getting smaller, then we get to microns. And around a micron, or this micron range, is where we have infrared light, and then close to that is visible, and just below that we have UV, ultraviolet light. So we tend to think of light as only really existing inside this window because that's what we see, but of course light can take on a whole bunch of much broader set of frequencies and wavelengths. And so this is the part of the spectrum that describes that. So let's wrap this up by pointing out that if you keep going smaller, eventually you get to the nanometer scale, and at this point then we start to talk about X-rays. Yes, this is X-rays that you see in doctors' offices, and that might be coming from astronomical sources. And then if we keep on going, we go to gamma rays. All right, so in the early 1900s, light was seen as a wave, and all of these properties were, at the time, supposedly well understood. The last thing I'd like to say at this point is that light was also seen to carry energy in such a way that thermal radiation occurs. And by this I mean that all hot things emit light. And you perhaps have seen this before or felt it before on a hot stove, or when certain things burn, you can sometimes feel the heat from it, not so much from the convection or conduction, but from radiation. And the peak wavelength of that radiation follows a very simple expression, and at the time it was understood to follow a constant, 0.29 approximately, times 10 to the minus 2 meters times Kelvin, divided by the temperature in units of Kelvin. All right, now where does this really come into play, come into the story? Well, here's where it gets interesting with the history. About 1900s, there were also many new electrical objects being, well, not objects, electrical devices being developed, and these included the light bulb. And both in the U.S. as well as in Europe, and especially in Germany, the companies that were producing light bulbs wanted to understand them and optimize them. And one of the famous men we'll talk about is Max Planck, and his job was to describe the physics of a light bulb. And of course, at the time, a light bulb was not an LED or a fluorescent light. It was an incandescent light bulb, which meant that it operated by a filament that was burning. And that burning little wire, this filament, would get hot and then produce light as well as heat. And then this was the light bulb. And some of you have seen this before, right? At least I hope all of you have. All right. So this is the beginning of the 1900s and the view of reality, at least as far as electrons and light goes, at the time. So this was sufficient at the time, but it was incomplete. And I'd like to show you it was incomplete by talking about 3 challenges to this. And these challenges are ultimately what led to the development of a new kind of physics that we call quantum physics. And that quantum physics is especially important to nanoscience and nanotechnology. So let's talk about the first of these challenges. So the first challenge, and these are challenges to classical physics. So the first challenge has to do with something called the ultraviolet catastrophe. And what this means is that in the understanding of the time, if classical physics is used to describe the radiation of light from a heated object, then what should happen is that a curve would look something like this that describes the amount of light versus wavelength. And so, for example, this could be 3 microns. This could be 2, 1, and then this would be 0.5. And on this scale, at least, this would be roughly the range of visible light. All right. So, if what this at this time, there was a view that the amount of light radiated from a heated object B would follow some constants times the temperature, T, and then it would be divided by the wavelength that would be produced to the power of 4. And so that's this curve here. All right, and so as an example that's real specific, if we had a piece of steel and this is the radiated light B, by the way, if we had a piece of steel at 5,000 degrees Kelvin, which is of course very hot, then we should expect that for shorter and shorter wavelengths, more and more light would be radiated. And that's a nice equation. We can calculate it, and for some regimes, that actually does work well. But what was noticed, and this is the catastrophe, is that in fact, for a particular temperature, a piece of steel would not follow that curve, but would rather bend down, something like this. And in fact, it kind of makes sense. This classical theory equation goes to infinity for small wavelengths, right? And so it would suggest that any object with any temperature at all would be spewing out gamma rays and X-rays and maybe even ultraviolet light. But actually we know that doesn't happen. And so that is the catastrophe, that the classical prediction is going off to infinity at short wavelengths, whereas the reality is that it bends down. All right, so this is the reality. All right, and so this is a brief sketch of the ultraviolet catastrophe, which was understood and known at the time. And in fact, one of the jobs that Max Planck had at his company, his light bulb company, not his, but he was working for a light bulb company, was to resolve this difference. All right, so the second challenge to classical physics was about the atom itself. And in this case, we're going to begin with the Rutherford atom. And the Rutherford atom was this idea that there is a positively charged nucleus with orbiting electrons. And let me use a different color here. And for example, for an atom with 3 electrons around a nucleus, then this is the picture of the Rutherford atom. Now, I have to admit, and this was understood at the time, that this model is a whole lot more accurate and useful than the models that came before it, stretching all the way back to many thousands of years to the initial ideas about what matter and stuff is made of. So it has some good features that are correct. It has a positively charged nucleus. It has electrons around it. But there's a problem, and that problem is that even though this looks like a solar system or planets going around a massive star, and it seems like that should be possible, it's not. And it shouldn't be possible because that Maxwell and his equations teach us that all accelerating charges must emit radiation. Or another way to say that is lose energy. Right? And so the picture that that leads to is that this is the Rutherford atom, but the reality is that if you started out with a positively charged nucleus and then had an electron going around, it would have to accelerate in a centrifugal way by bending, and that's an acceleration, in fact. And by bending, it would have to lose energy and slow down. And by slowing down, it would have to get closer to the nucleus. And then eventually, this would keep spiraling so that every electron in the universe would have to collapse in on the, every electron would have to collapse in on the nucleus, and as if all the planets were collapsing into the star. And no, of course we know that's not happening. And so this is the second challenge to classical physics. So let's turn to the third challenge. The third challenge is something really cool, and I hope that you appreciate this. So this is the challenge number 3, which we'll call the photoelectric effect. And this brings in someone we all know, Albert Einstein. And he had a part in this that led to his Nobel Prize a few years after this. So this is in the early 1900s, and at that time it was known that when light is incident on certain metals, for example, potassium, and let me draw that. And I invite you to draw this with me. All right, so if this is the metal, so it was known that, of course, you can shine light, and I'll just draw a wiggly line here for the light, and let's say it's red light. You could shine light on the metal, and many metals are kind of shiny, right? Not all of them, but many of them are shiny like a mirror, and of course they will reflect the light itself, right? But some metals have an interesting property, and we'll get to that in just a moment. So red light shining on potassium will generally lead to the reflection of light, but nothing with regard to electrons. So that's really important. No electrons coming out from the metal when red light is incident on potassium. Now you may be thinking, well, no kidding, right? But here's the interesting thing. If there's green light incident on the metal, then something really cool happens. An electron, or a series of electrons, can emit, and those are called photoelectrons. And just because the light was incident on the metal, in this case with this wavelength that's green, electrons get emitted from this piece of metal, right? And those electrons have a certain velocity. I'll call it V1. And then lastly, if we keep, the other thing that was observed is that if we keep adding, let's say, a blue electron, and I know I'm getting crushed here on the side, also electrons can be generated with another velocity or another kinetic energy. All right, so let's review what I just said. If you have a piece of metal and you shine light on it, different things happen depending on what the wavelength is of the light or the frequency. If you shine red or low frequency light on it, you get no electrons. And actually you get no electrons regardless of how much red light you shine. It doesn't matter how much light you shine, it matters that it is red versus any other color. Now if you increase the frequency to green, make it a shorter wavelength, then electrons can appear. And they emit, they jump out from the surface into, for example, a vacuum with a known frequency that can be measured and a known kinetic energy. And then lastly, if you keep increasing the frequency or lowering the wavelength, you can also continue to get electrons, and in this case, the kinetic energy or the velocity of the higher frequency light will be greater than the lower frequency light. All right, so I hope you see what I'm saying here is that the shorter the wavelength of light or the larger the frequency of light shining here, the more energy these electrons have. And there's this threshold. There's a threshold of what frequency will produce any electrons at all. All right, so there's two parts to this. There is a threshold, and I guess I misspelled threshold. 2 H's here, 1 H here. I think the 1 H is correct. You decide what you like. There is a threshold frequency below which no electrons will emit. And then B, the maximum kinetic energy has nothing to do with the light intensity, only the light's frequency. Okay, so this is the photoelectric effect that was known by the time of Einstein, and Einstein came and said, ooh, I have an answer for this, because classical physics cannot describe this effect. This is really a weird thing. All right, so we're going to return back to Einstein and his answer to this that led to the Nobel Prize. But before getting to that, I want to talk about Max Planck's answers and ideas to what's going on inside an atom.